Now let's get started. Okay. Hi everyone, my name is Hengtong Kang. Today I'd like to talk with you about 3D point cloud. And the title here is 3D point cloud classification based on adaptive key point selection PointNet. Okay, what is point cloud? While looking at the left image, this image actually it is not optical image. It is created by 3D scanner named LiDAR. The light ranging detection and ranging. And the right part, the point rabbit, right? So what is point cloud? Actually, point cloud is some points describe the shape of the object. Okay. So let's move to our problem today. The problem here is point cloud classification. That is, if the input image is a point cloud, maybe an airplane, and can our neural network tell whether it is a ship, a car, or an airplane? Okay, so the task is clear. It is point cloud classification. Actually, there are many approaches. Many pioneers have explored these areas, but PointNet, the leader one, to use a neural network to directly process a point, rather than using the 3D CNN, which is computational costly, or use some kitty trees, which is not very high accurate. So here, let's talk about PointNet. Actually, the mechanism of it is really simple. For example, we treat our point as 3 channels, X, Y, Z, and we use multiple layer perception to process each point. For example, if the input is n by 3 here, and when we reach here, we can get n by 1024. And here, 1024 is our feature vectors. After that, we'll apply max pooling operations on these vectors and get 1 by 1024, which is used as global features for downstream tasks like segmentation, network, or classification. So that is PointNet. However, PointNet has a problem. That is, it can only extract the global features. That's why PointNet++ came here. Well, for PointNet++, it firstly used a method named farthest sampling method to sample some key points of the input point cloud. And after getting the key points, it will set the key point as anchor point and then search around here within a certain radius. After that, we can get many grouped point cloud, which will be recursively processed by our PointNet. Pretty easy, huh? Actually, PointNet++ has the same authors with PointNet. But PointNet++ still are not elegant because they use the farthest sampling method, which is based on our human knowledges. So that come up with our new models. Can we let the machine to determine whether the key point it is, rather than using a man-made method? So that our new model is that we will replace the farthest sampling method by neural network. So we input is the input is point cloud, and then output is a key point. Using the key point, we'll do the same steps as PointNet++. Search around, get a group to PointNet, point cloud, and process by PointNet recursively, and then get the result. That pretty clear, right? So let's sum it up. So in our whole work, we design a novel deep neural network to adaptively select key points that are task-specific. And we also design an objective function to optimize generated key points. And for the result, we almost obtain the same result using a more simplified neural network. Come to our objective function, we can see that our objective function composes of two parts. Left part, cross entropy, right part, transfer loss. Well, since our task is classification task, so it's commonly to use cross entropy. Well, why do we use transfer loss? We want to use transfer loss to restrict our generated key points to interpret our shape of the input rather than generate random points, right? Now let's move to our evaluation. We did 5 experiments to evaluate our models. The first one, overall classification accuracy. We compare our model with other 4 models, PointNet++, PointNet, MBCN, and subvolume. And we can see that our model could get 90.7. That is equal to PointNet++, and better than the other 4 models. Well, the state-of-art result is over 93. So we still have a long way to go, right? Well, as for another experiment, there are many hyperparameters like the number of gain, the value of radius, and the number of key points. So in this experiment, we set the radius to changing, the other parameters stable. And radius is changing from 0.7 to 0.3 with step size 0.1. And accuracy, you can see, is decreasing with a decreasing radius, which means if we want to get a great result, we should select a great radius. Now another experiment, a regularization term. Well, the left upper, we can see the right point here is generated key point, and the blue points are original point cloud. So looking at the images, learned key points can almost represent the our input point cloud. But looking at the lower ones, the generated key points are either spread out or clustered together, which means if we don't add the regularization term, the learned key point is useless, right? And the curve can also show that the blue curve represents the one with regularization term, so the accuracy is always higher than without regularization terms, and the validation loss is lower. And the other 2 experiments are almost the same as the radius one. We just keep the gain the same, or keep key point the same and change the other hyperparameters. We can find out that when we set our gain point as 200 and the key point as 16, we'll get the highest result. Okay, let's sum it up. We propose a novel model that could adaptively select key points, and our model is able to extract task-specific features. The proposed model is general for tasks require key points. Okay, let's move to our code part. The main function lies here. Here is our packages. Here we input some models, and here is our data loader because we use the PyTorch. Data loader is really important. And here is our training, and here is our evaluation. And here's the main function. Now let's move to our training function. During each epoch, we sampled the batches from the data loader X, the data Y, true, the label, and then we input the data into our parallel model. So what is our model? It lies in the model folders. PointNet, adaptive assay. Okay, since it's PyTorch, we just need to see the forward. We will get the coordinates from the heads. This another encapsulated functions, and after getting the coordinates, we will use the ball query to get our grouped point cloud, and then the grouped point cloud will be processed by our encoder and to obtain grouped features, which will be processed by mux pooling and get global features. Then the group features will be sent to MLP to get the classification result. Here we must mention that we have calculated the chamfer loss, and which will be added as our regularization term, city loss, which is rotated here. Without it, we multiply it by 0.0. With it, leave this one out. Okay, that's all. Thank you.